Okay, so if you're having to watch this from home today, we're going to take a look at quantifying conservation of energy using those bar graphs that we've been working on in the previous assignments. I'm going to show you now how to quantify it. Just to help me remember, did I talk a little bit about conservative and non-conservative forces last week? Did we do that? Okay, so we have that portion done. Where I haven't done anything is actually quantifying energy using the law of conservation of energy. Let's go ahead and try this. We had at least a few groups survive the 6.1 meter drop. Everyone had to calculate your speed of their egg drop device. I'm going to show you that there's a far easier way to calculate impact speed than the way I showed you guys in the first unit. So we're going to do this via energy principles. Okay, so we're dropping from the balcony. We have our egg drop project. And that egg drop project accelerated due to gravity here and then hit the ground at some speed that you had to determine. If we do this using energy, you'll see that it can be done very, very quickly, very simply. So the kind of energy that it has up here, using a bar graph idea, is that you've got E sub gravity, you've got E sub kinetic, you've got E sub elastic, and you have thermal. E thermal. Those were the kinds of energy that we had on that energy storage diagram. Now, this is all gravitational at this point. And whereas in our activity, you didn't have to quantify things, you still had to look at where that energy went from one form to another. I'm going to say that that's 6 blocks there. And then right down here, if we are ignoring things like air drag and that kind of stuff, which you did for your egg drop, all of that energy here would have been turned into kinetic energy. And so if we don't have any energy loss, then if we had 6 blocks of gravitational, we should have 6 blocks of kinetic. Now my goal here is to quantify that speed. So let's go ahead and just write some equations out here. I see that the final kinetic energy should be equal to the initial gravitational energy. So if our energy just changes from one form to another, I can go ahead and quantify that kinetic energy as 1/2 mv squared. That's equal to the gravitational energy I started with, that's mgh. And then those of you that are keen math students will recognize right away that I don't care what the mass of that object is. The 150 gram egg drop project should behave just like a 250 gram egg drop project. The masses reduce objecting.
So that 1/2 mass loss times square root is the kinetic?
That's the kinetic energy, absolutely, yep. So kinetic energy, 1/2 mv squared. So if I'm going to use energy principles to solve this, I do have to know what kinds of energy those are, and then of course each of those forms of energy have an equation for them. Okay, so 1/2 mv squared is what I end with. I started with mgh. I reduce out that m. I'm solving for v final, so I'm going to go ahead and multiply both sides by 2. And then since I'm looking for v final, I take the square root of both sides. Now, I think for your egg drop project, I had you guys use g as 9.8 so you can get a more accurate answer for the speed instead of using g is equal to 10. 6.1 meters for that drop height. And again, once I have those numbers put in there, it's not too bad just to go ahead and multiply everything out. I'm getting about 10.9 meters per second. And you notice I can do that really quickly with just using energy principles. Now, I know I had a couple of groups that survived the 6-meter ground. Raise your hand, you survived the 6-meter ground. Kayla, where's yours over here? All the way on the left? Bottom right here? Hey, I'm gonna, people can't see this because it's small, but you calculated exactly the same speed. You got 10.9368 meters per second. That's basically what I have there. You just had to go through and determine the time it took for it to fall, which you can do 1/2 gt squared, all that kind of stuff. And then you had to plug that into the velocity equation, v is equal to g times t. You can do that. Somewhat complicated to do that here. Fairly easy to do here using energy principles. So energy is a great simplifier. It just makes things easier to do, right? So again, that's a way to do it. All right. Let's take a look at this one here. A ball is thrown upward at a speed of 25 meters per second. We'd like to know how high it goes. So again, if I were to draw something like this here, I might say it's a baseball thrown upward with some initial velocity, vi equal to 25 meters per second. It's rising, it's coming to a stop way at the top. If I were to go through and draw the little bar graphs, which is what we have done a fair number of assignments on, this starts out with kinetic energy. Let's say that it starts out with 6 units of that. There's also gravitational potential energy. There could be elastic. It could be thermal. At the very top, that energy should transform completely into gravitational. And just like we did before, it's like the reverse of the egg drop project. mgh final should be equal to 1/2 mv initial squared. So the final gravitational energy should be equal to the initial kinetic energy. For those of you, again, that are really good math students, you see that the mass reduces out. I'm solving for how high it goes, so I'm going to divide both sides by g. Comes v initial squared divided by twice of g. Plug those numbers in. And again, with just some quick calculations, 25 squared, divide that by 2, divide that by 9.8, I'm getting about 31.9 meters. And we can quantify energy fairly quickly with those equations and solve some things that probably prior to this we'd have a hard time doing. These next two are just called enrichment questions. They're not something that you'd see on a test or a quiz. You won't even see it as part of your project, but it is sometimes good to dig in and see what you're capable of doing. I want to give you 2 minutes of just independent time to see if you can go through and figure out how to solve this question. An apple falls from a tree, a distance of 8 meters. It hits the ground with a speed of 9 meters per second. What we want to do is determine the amount of energy loss due to things like air drag. I'd ask you to start with just drawing the bar graphs. Starts with what form at the top, what does it end with, and then make sure that you include that there's some thermal energy loss, right? And that's from air drag. Try that, and then we'll set up the equation and go ahead and solve it. 2 minutes, see if you can do it. that's our 2 minutes, and I'm going to go ahead and show you how to solve something like this. It's a challenging question, but hopefully you had a chance to be able to draw the bar graphs. So let's go ahead and start with that. So up here at the very top, we should have gravitational potential energy. And so again, it's somewhat arbitrary, the number of blocks that we're given it here, but it starts with E gravity. At the very bottom, what we see is that we have lost some energy due to thermal energy. And so if I had 1, 2, 3, 4 up here, I'm going to say that I only have 3 of the kinetic, and that's because I've lost some energy due to thermal. Now, I'm going to go ahead and try to determine that. You might notice that thermal energy is the difference between gravitational and kinetic. So I'm just going to go ahead and do a TH would represent the difference in energy between these. And so let's go ahead and write that. This would be mgh initial. And this is kinetic energy is 1/2 mv squared. The difference between those would represent the thermal energy. Now I can't cross off the m's here, right, because it's not equal to 0 or anything like that over here, so I can't cross that off. I'm going to go ahead and just start to plug in some of those numbers now. And so let's go ahead and do that. That's 0.1 kilograms. I'm going to drop the units because of lack of space to be able to write everything up here. So 0.1 kilograms, 9.8 meters per second squared for the height, or for the acceleration, and the height was 8 meters. Just subtract from that 1/2 of 0.1. The velocity is 9 meters per second. We're going to square that, and then we can go ahead and just multiply those numbers out. So 0.1 times 9.8 times 8, that's 7.84 joules. That's 4.05 joules. The difference between those represents the energy loss. And so that's about a 3.8 joules of thermal energy that's been created in that process. Now, if I'm interested in knowing the average force of air drag, again, these are enrichment questions. You would not be expected to answer these kinds of questions on a test. If I wanted to figure out that thermal energy or the average force of air drag, we go back to the concept that work is force times distance. That work was 3.8 joules. That's work done by air drag. The distance that it fell, I think, was 8 meters. And so if I want to get that force, I just take the 3.8 divided by the 8. And that's saying about 0.47 newtons. And so that'll give us a sense of the average drag force, okay? Again, folks, you're not going to be expected to do anything like that on a test or quiz, but it's sometimes good to just see how those equations would all work out. Full year class, definitely. We would spend more time on that kind of stuff. But one semester, just consider that enrichment. How many people were able to set up the initial bar graphs correctly? Got this stuff done? Okay. Once you get that done, that sort of gives you the ideas of what equations are right, then we have to do some of that. All right, guys, let's go ahead and summarize this with one final slide on conservation of energy. Mechanical energy is not always conserved. Sometimes that energy is increased from extra work being done. Sometimes it goes out because of thermal energy. My grandmother always say, turn off the lights, Mr. Eisinger, you're wasting energy. And I was a smart aleck. I said, but Grandma, how can I waste energy if you can't create it nor destroy it? Not a very good answer to my grandmother. She grew up during the Depression era, so she was all about very, very cost conscious. When she says turn off the lights, that's because not all forms of energy are created equal. The left-hand side here represents the energy inputs, and again, we started this unit by talking about where we derive our energy from. coal, natural gas, petroleum, wind power, nuclear energy, and so forth, is all of our energy inputs. Our energy output, these are the things that we use to do things, right? Our residential, our commercial, industrial, and so forth. Well, there's a lot of energy that's just lost. And so conversion losses is that heat byproduct, if you will. Let's go ahead and summarize. Energy conversion is often necessary and it is inefficient. So if you have to convert coal into something else, you usually have to burn that coal. And so that burning is an inefficient process. Waste energy as heat is not that useful. It could be harmful to the environment. And so when we transform energy from one form to another, heat is invariably a portion of that energy that goes away. Why do we put power plants by water systems? So we dump that heat oftentimes into water. And water actually is a really good heat sink for us. But it can change that water temperature and it can affect that local ecology. You want to reduce the load, so turn off the lights. Improve efficiency, and a big part of this project is to measure the efficiency of your launcher. So make things more efficient. And then finally, a big part of R&D, that stands for research and development, is to develop new technologies to try to harness various forms of energy. So energy, again, is how we get things done. And the goal right now in the energy sector is to try to make things more efficient and improve technology. Okay? Guys, I'm going to put a line through this stuff here. We don't usually have a chance to get into this level of detail. So this is much more mathematical than what we'd like to go through and do. So I'm going to put a big line through that. And I do need to spend a little bit of time today developing a concept of simple machines. So it's our last topic for this unit. And so I'm wondering if anyone has ever used a car jack to change a flat tire. Raise your hand if you've ever used one of these things. A few people? Kayla, thank you. You're one of the few. Do they still teach you to do this in driver's training? Do they say, oh, you have to be able to change a flat in driver's training? They just make sure you have a number like AAA to call or something like that, right, for roadside service. But no, you've done this before? Awesome. One of the few. So the idea behind this is we use a car jack, not because I don't have the energy to lift the car, but simply I don't have the ability to exert the force necessary to do that. So the idea behind this is that Kayla would put this thing here underneath a strong part of the frame of the car, use this to turn the input side. And then as I turn that input side, what we would notice is that I have a really big distance that the arm moves through. This is going through like a circumference, if you will, of a big circle. And every time I move this thing through a big circle, I notice that the car jack goes up a little bit. And the idea behind this is that simple machines are ways of making forces bigger at the expense of making distances smaller. And so a jack like this is sort of a force multiplier. So I can lift up a really heavy car without having to exert a tremendous amount of force. And I'd like to show you how that works using this. So what these things do is that they change how force and distance act. So simple machines are force distance multipliers. If you get a jack, you need to use, if you get a flat rather, you need to use a jack because you don't have the capacity to exert force. So because you don't have the energy to lift the car or you don't have the force necessary, this is the right thing. You just cannot exert the force necessary to lift it. Most machines will multiply force. They will make force bigger, but they cannot multiply energy. So they don't make the energy output bigger. They just make the force bigger. If they make the force bigger, that means that the distance has to become smaller. And I'm going to do that with a couple of demonstrations, show you that with a couple of demonstrations, and also show you a little bit of mathematics on it. Okay, I want to draw a little block diagram for you to show you sort of a theory on how machines work. There are 6 simple machines. I have posters on the back wall. They're covered now by my egg drop projects from my first hour, but They are the wheel and axle, the lever, the inclined plane, the pulley, the wedge, and the screw. And so those simple machines allow for work to be done more easily. There's an input side to these. So let's go ahead and draw an input arrow. The input arrow represents work done on the input side. What a machine does is it allows you to do work on the input side, and that machine will transform that into output work. So let's use some color coding to show that. So now we have work on the output. Kayla has used a jack to lift up a car before. Kayla exerts a force on the input side through a really large distance. And so usually what happens is we have a relatively small force acting on the input side through a pretty big distance. And what the machine does is it transforms that into a smaller output distance, but through with a much larger output force. Now I'm changing the order of F and D. That's just a product. But you notice what happens is, ouch, I have the output force become a lot bigger. So that's an increase in the amount of output force. But that comes at the expense of the distance becoming smaller. And an increased force means a much smaller distance. Now, I'd like to demonstrate that really quick with a lever. So I want to actually go through and do this one here. It doesn't make for really good video recording, so if you're having to watch this from home, sorry, there's going to be about 10 minutes or so, 5 minutes or so of this demonstration. Come around here for a minute. Come on up really quick. I'm going to have you help me with some of this.
Me?
Yep.
Okay.
Since you're close by here.
Okay.
All right. First, just tell me how heavy that thing is. Just say it's really heavy.
It's really heavy.
It's really heavy. Yeah, this is a 15-pound ball. Now, I'm going to use a lever to lift that thing. Now, this lever is just designed to change the direction of the force that I have to exert to be able to lift it. So, Seppi's going to try this for me. Okay, are you ready?
Yeah.
Okay, now I'm putting the fulcrum. The fulcrum is the pivot point, if you will. I'm putting the fulcrum right smack in the middle of this thing. So what I'm going to have you do is push down on this thing with a single finger. No, you can use more than a finger if you want to. But push down on that thing. Use 2 fingers. Use your whole hand. All right. You're having to exert the entire weight of that bowling ball on that because of where that fulcrum is located. So you said it was really heavy. Push down on that thing. Would you agree it's pretty heavy?
Yeah.
The value of this machine is that you can push down to lift up, right? All that fulcrum is doing is just changing the direction of the force. You push down, it lifts up. Now, add those things to this on both sides of that, one at a time until you're able to lift it. Because of where that fulcrum is located, you notice that the input distance is how far this moves down is the same as how far the output goes. Do you guys see that the distance there is the same? Okay, so there's no increase or decrease in the output distance compared to the input distance. So you have to put the entire force of that thing on there. How many is that? That 10? That's 12?
Yeah.
Okay, now just one at a time now. And be careful because if this thing topples, I don't want it to fall on you. Okay, good. I saved them. You're welcome. All right. We had to put how many? Is that 14 of those things? Each of those are half kilo. That's like 7 kilograms of weight to be able to take those things off. Be careful. Oh. Okay, now. The advantage of that machine was simply to change it downward force to an upward force. Now what we're going to do is we're going to create something called mechanical advantage. I'm going to move this closer to that. Now you notice something. When Seppi pushes down on this, go ahead and push down on that. You notice, first it was easier, wasn't it?
Yeah.
You can see that. You notice how far this thing moved down compared to how little this thing moved up. This for a second, so people do that again for me. Look how little that moved up compared to how far that went down. That's what we call mechanical. That's what we call mechanical advantage. Okay. Now we're going to try that. Thank you, Ben. You were so quick. You're going to put those things on there, one at a time, and see how much of a mechanical advantage we get here. Okay.
It's already like moving on this too.
It took 14 before. Now we need 4 of those. That's crazy.
Yeah.
That's what we call mechanical advantage. Super exciting. I can see that. All right, I like it. Thank you. How about 2 claps for Seppi? Thank you. And 2 for Ben. For just about saving me on that one. All right.
How much would that would have been 14 too?
Yeah, so now we've sort of made mechanical advantage of less than 1. My gosh.
You're like 20 pounds.
That'd probably be about 50.
Oh, actually, yeah.
All right, let's go ahead and take a look at this, folks. Again, our goal is to summarize this stuff using ideas of work and mechanical advantage. Performance of a machine is described by something called MA, mechanical advantage, and so we're going to now quantify that by looking at just how effective that machine is in making force bigger. So there's 2 kinds of mechanical advantage. One is an ideal setup where we sort of ignore energy losses, and then the other is an actual where we have to consider the fact that we're going to have some losses of energy. Machines are all about work changers. So let's say this is that work is a product of force and distance. What I'm going to do is I'm going to take a ratio of the distances. So on the left hand, or the stuff that we looked at prior to this, is we see that the distance becomes smaller when I use a machine like that. Let's go ahead and take a look at that ratio of the distances. So we're going to define IMA as a ratio of an input distance compared to an output distance. So how far Seppi moved the input side compared to how far the output side went up. For this example, you push the long arm down 1 meter. So he exerts a force on this side that's 1 meter of distance. And then because the fulcrum is located really close to the load, that other side of that only lifts us up about 0.2 meters. If we define mechanical advantage ideally as a ratio of input to output distance, then the IMA here would be 1.0 meters divided by 0.20 meters. And we see that the IMA is a pure number 5. Just based on where that fulcrum is located. 1 meter down produces 0.2 meters up. That ratio is 5. We'd say that the IMA is 5. Now, the other side of that equation, I noticed that the force became bigger on the other side of that. The AMA has to do with the ratio of forces. So the AMA is a ratio of how big the output force is to the input force. In this case, Seppi is lifting up that boulder by exerting an input force of 250 newtons. And then based on where that lever is located, that makes the output force 1,000 newtons. So I'm able to lift a much heavier boulder. The AMA would be a ratio of 1,000 to 250. And that is a pure number. In this case, it would be 4. So the actual mechanical advantage, we're always going to see that the IMA is greater than the AMA, and that's because we always have some sort of internal friction. That's going to reduce some of the energy on the output side. I think I have just enough time to show you how to calculate efficiency. And so efficiency is always a measure of output work to input work. Let's go ahead and do that now. I'm going to use color coding again for this. We said that the output work was D out times F out, so let's go ahead and do that in red. I'm going to lift this up so we can see it better. I'm going to divide that now by the input work. We use blue for that. I'm going to show you how the associative property in mathematics are often used, the associative property in this case of division. Instead of grouping the F out with the D out, I'm going to go ahead and group the forces together. So I'm just going to put some parentheses around the F out and the F in and consider those as a grouping. Now I lifted this up so you can see it better in the back. F out divided by F in, I think it was described over here. What is this kind of quantity, F out over F in? It's over here. Is that what we call the AMA? Okay, so this right here is the AMA. Can you look and tell me what is this side? What is D out over D in? And don't say it's the IMA, because it's not the IMA. Do you see it, Cannon? What is it? Say it's mechanical advantage. It's close to the IMA, but it's not the IMA. You guys see that it's the reciprocal of the IMA? Do you see that it's the reciprocal, the IMA inverted? Well, if I multiply these two things together, what I get is the efficiency is the AMA, the actual mechanical advantage, divided by the IMA, the ideal mechanical advantage. And so it's a way of calculating the efficiency. For the example that we did above, if the AMA was 4 and the IMA was 5, that efficiency would be 80%. And so we would say that that is an 80% efficient machine. Okay? Folks, we're going to do a little bit more with machine stuff tomorrow. We are near the end of this unit, and so we just have to be aware of that. And then we do have to start building our project next week is when we're going to start building that launcher. So I'm going to go ahead and stop there. No new assignments, but some of you still